Hi everyone, here's your Sioux Falls physics teachers again, and welcome to our problem on RC circuits. We have a 100 ohm resistor and a 1 farad capacitor connected in series to 6 volts as shown in the diagram, and we have a number of items to determine about the circuit. The first is the time constant. And again, remember that this would be related to the amount of time that it takes to charge. And the time constant, remember, is simply the resistance and the capacitance multiplied together. So we have a resistance value of 100 ohms, a capacitance value of 1 farad, and that means that our time constant would simply be 100. And again, we won't go through all of the dimensional analysis on the labels, but we can show simply enough that if we have ohms and farads, if we replace those with their equivalents, that they actually, when multiplied together, do produce a label of seconds. So our time constant then is 100 seconds for this circuit. The next problem asks for the maximum current through the resistor. And again, we treat this problem the same way we would finding any current amount, and that is to use Ohm's law, or V equals IR. The voltage here is given as 6 volts. Our resistance is 100 ohms, and so we can calculate the maximum current from this equation. And we find that we have a maximum current of 0.06 amps. Notice, although the problem does not specifically address this, that maximum current would occur right away at the beginning, because at that point there is still the full 6 volts that is producing current through that 100 ohms. As the capacitor slowly charges, the amount of voltage across the resistor would be less, and so that current would become less as well. Next, it asks for the maximum charge stored on the capacitor, and notice that the maximum charge, of course, would occur at the end when the capacitor is fully charged. However, for our equation, we use our usual equation for capacitance. It is equal to charge per volt. We have a capacitor of 1 farad, and again, the voltage is 6 volts. And so our maximum charge, which will occur at the end when the capacitor is full, turns out to be 6 coulombs of charge. Hello everyone, here's your Sioux Falls physics teachers, and today we're looking more at RC circuits. We have 3 33 ohm resistors connected together with a capacitor in the arrangement that is shown. First, we're going to take a look when the switch is closed, and then we'll look at when it is actually open. To begin, we want to notice that the main issue is that the way the capacitor is arranged with the resistors means that the capacitor is not connected to the full 6 volts of the battery. So we want to deal with our resistors, and again we'll label them as 1, 2, and 3. And the first thing that we want to do is find the equivalent resistance from that. Now notice that resistors 2 and 3 are in parallel. Parallel, we use the inverse. So if we take 33 ohms and 33 ohms again, we find that our resistance for 2 and 3 together is 16.5. That allows us to then simply add to resistor 1 because 1 is in series with those two. So we now have 16.5 ohms added to 33 ohms. and we get a total of 49.5 ohms for the circuit. Now the reason that this would be important is because it allows us to eventually find the voltage that will be applied over this portion of the circuit. So first we want to find what our current in the circuit is. We would do this by applying the equivalent amounts for the entire circuit. 6 volts is our voltage for the entire circuit, and we just calculated our equivalent resistance at 49.5, and we find that the equivalent current is then 0.12 amps. Now the part that we're interested in is the part where the capacitor is at. So next we want to apply that to resistance 2 and 3. So we would go back to our equation of V equals IR, but this time just apply that to 2 and 3 together. Notice that the 0.12 amps would still be the total current for the two, and that our resistance, as we calculated earlier, is 16.5. That leads us to the fact that this voltage is 2 volts. Notice that that makes sense because this portion of the circuit here containing resistors 2 and 3 has a lower overall resistance and therefore needs a lesser amount of the total voltage available. Finally, now that we have the voltage of that part of the circuit, we can go back to our basic equation of capacitance equals charge per volt. The capacitor has 0.025 farads, and the voltage amount that we now apply to the capacitor is the 2 volts. So our charge is equal to 0.05 coulombs. And notice that that is for the situation when the switch is closed. Now the next portion asks when the switch is open, which is actually how our diagram is drawn here to show us. When the switch is open, then that basically means that resistor 3 here is not part of the circuit. It is not attached. Resistor 2 and the capacitor, however, are unaffected. The nice part about this is that it actually makes this problem much simpler because this time we will not need to do any calculations to find the voltage across the capacitor. We have now 2 resistors, 33 ohms here and another 33 ohms here. So the voltage that is used is now split evenly. So if it is 6 volts for the total circuit, divide that by 2, and we now have 3 volts that is applied to that portion of the circuit, so now they are sharing that voltage evenly. Now we can simply go back to our equation of capacitance equals charge per volt. The only change is that this time the voltage that is applied to the capacitor is 3 volts instead, and we get our total circuit charge of 0.075 coulombs stored on the capacitor in this situation. Hello everyone, here's your Sioux Falls physics teachers, and if you click here you must want to know more about internal resistance. Here we have a battery of EMF 6 volts and internal resistance of 0.1 ohms. It is connected to a lamp of resistance 4 ohms. We need to draw a schematic and determine the terminal voltage of the battery. We'll begin with our schematic for this situation. And remember that internal resistance is simply attached to the battery. So it is basically in series with the rest of the circuit. So here we can continue on. Here is a resistor for our lamp, and that then gives us the total amount for the circuit. Notice that it would be very common to outline the battery by putting the internal resistance and the EMF together. We also would want to include some labels: internal resistance of 0.1 ohms and EMF of 6 volts, and then our external resistor is 4 ohms. When it says to determine the terminal voltage of the battery, the first thing we will need is the total current flowing through this circuit. So we need an equivalent resistance for the entire circuit. And again, remember that it's pretty common to show the internal resistance as lowercase r. So we would simply add lowercase r to our other external resistance, and that gives us 0.1 ohms plus 4 ohms for an equivalent resistance for the entire situation of 4.1 ohms. Then we can use that to calculate the amount of current in the circuit. And again, when we say equivalent here, this time we are talking about 6 volts, as in the total voltage, the EMF supplied by the battery. This is not necessarily the same as the terminal voltage, as we'll calculate here in our next step. So we would use that 6 volts, apply that to the 4.1 ohms, and we get an equivalent current of 1.46 amps. Now our last step would be to use that equivalent current amount to find the terminal voltage. And again, remember that terminal voltage is simply from this positive terminal to the negative terminal. And so we can think of that as being the voltage applied to the 4 ohm resistor. We can use our same Ohm's law equation of V equals IR, and we have the 1.46 amps. That would be the current through the 4 ohm resistor, and then the 4 ohm resistance for the lamp. And if we multiply those out, we find that our voltage, which can be described as the terminal voltage, is actually 5.85 volts. So again, although the battery itself supplies 6 volts here of EMF, if we were to actually measure the circuit to see the amount of voltage that is supplied to the external circuit, we would get a value of only 5.85 volts. Hello everyone, Sioux Falls physics teachers looking more at internal resistance. In this case we have 3 10 ohm resistors connected to the battery, which has an EMF of 12 volts, and this produces 0.39 amps of current. The first step here is that we want to actually calculate out what the internal resistance of the battery is. So what we would do then is look at the total current that we have available and apply that to Ohm's law. So we have equivalent amounts for the entire circuit. 12 volts is the EMF of the battery. 0.39 amps is the current that has been measured. And if we work out the algebra, we find an equivalent resistance of 30.77 ohms. Now, if we want to find our value for internal resistance, remember that the equivalent can simply be found by putting everything in series with the internal resistance. We already have 3 10 ohm resistors. So 30 ohms for that portion of the circuit. And then our unknown is the internal resistance. So if we had a total of 30.77 for the equivalent and 30 are accounted for by the external circuit, then the internal resistance must be 0.77 ohms of resistance. The next portion of our problem asks to calculate the current and terminal voltage if only two 10 ohm resistors were connected instead. So now we can eliminate one of these over here. Our circuit is only going to include two 10 ohm resistors. And so as we calculate our equivalent resistance this time, we will have 20 ohms from the external circuit. Notice that the internal resistance should not change, so that's still 0.77, which means that our equivalent resistance for the entire circuit is 20.77 ohms. This would then allow us to calculate the current in the circuit by using the equation V equals IR and applying it to the entire circuit. We have 12 volts, and our new equivalent resistance with only two resistors is 20.77, and that gives us an equivalent current of 0.58 amps. Finally, it asks for the terminal voltage in this situation. And again, we can find that by applying V equals IR to just the external circuit amounts. So between points A and B, we have a total resistance of 20 ohms. So we can take the 0.58 amps of current in the circuit times the 20 ohm resistor, and we end up with a voltage for the external circuit of 11.56 volts that is actually applied to the two 20 ohm resistors.